Programming loops are quite common assets, no matter the language used. Whenever a set of commands has to be rerun, they are the basic choice. By default, the shell runs the scripts line by line, one at a time in the order of their appearance. According to this rule, each command has its turn only once. However, modern versions of Unix interfaces are changing this rule, thus providing a strong support for structured programming. Our main objectives in this lesson are to define a program loop, to learn how to control program loops using the while statement, control the program loops using the until statement, control program loops using the for statement, break out of a program using the break command, bypass the remaining of a program loop using the continue command, and we will also cover how to exit a script using the exit command. And finally, we'll use the select loop to build a menu of options. A group of commands meant to be executed in a repetitive manner can be identified by the special keywords do and done. The entity that controls how many times this sequence is iterated is found before the do. We will refer to this line as the loop controller. We'll see that the Unix interpreters family offer three major types of such iterative constructions, and that would be the following. While and until, considered to be a standard entry control loops, the for do done, known as the loop with a limited number of iterations, and that is not all. There is a fourth type of programming loop only available in POSIX compliant shells, and that is the select loop. Constructions that are based on while syntax are by far the most common in shell scripting. We assert that the while command is based on the verification of a logical state of type true. What this means is that, unlike the syntax of the homonymous procedures in other languages, the control of this loop is not done by checking a purely logical condition, but rather by checking the return code of a system command. So whenever this state is identified as true, the repetitive sequence encapsulated between the do done is then executed and the process is run again using the same order of commands until a false state is returned. This kind of programming approach forces us as programmers to be quite careful and to anticipate at each cycle the refresh of the triggering condition, that is the while structure controller. Otherwise, the danger of running infinite loops appears. Now, in the present image, you can see the fact that there are several ways to implement a while sequence. The so-called infinite loop, standard command-controlled while loop, logically controlled loop using the test command, loops controlled by a typical arithmetic expression, variable controlled loop, standard output control loop. These definitions of the control structures, all using the programming loops in shell scripting, give a plentiful universe of test cases which we can benefit from. You hereby can see a pretty comprehensive list of different ways to define a while loop in a script shell. While the points B and C are most often used, it is not excluded to meet one of the other forms. The first in the list, which seems quite dangerous, is also a commonly used implementation, provided that usually in the do done section of the code, which again is controlled by a while true element, you will always find somewhere a particular break command, which we'll cover later on. Here is one of the simplest implementations of a while loop, controlled by an arithmetic expression. Note at the 8th line the systematic refresh of the operating context of the loop. Okay, now such a scenario will output this data. And here we have an interactive test to be ran directly from a text console. I have deliberately skipped the control of my while sequence to demonstrate on purpose a basic technique that can be of use when testing programming loops in a hurry. This is about issuing the Ctrl-C combination, also known as the command interruption sequence. Now, this third example, an interactive shell, shows how a set of several commands can equally serve for properly controlling a programming loop. Note, however, that the exact moment of the control state detection occurs precisely after the last command has been completed, before the do keyword. So be aware with how at each loop several commands, in our case the print command, are rerun. This could flood our standard output with plenty of text, so be advised. This type of implementation places the effective control outside the loop itself, which increases the risk of running in an infinite loop. A precautionary measure here is the presence of the read command in the list of the control sequence, which performs an interruption of an otherwise continuous execution and which gives us a means to decide whether we want to break the loop or continue. The until type of loop construction has also a control structure with detection at the loop entrance. Not very different in implementation, except that it operates in reverse logic than the previously studied case. In contrast to what we've seen in the while loops, where the actual command sequence is executed after each run of the control structure, in this case, this is run before the effective control expression is validated. One of the significant differences is that, unlike in the while loops, where it is possible to advance in the script without executing at all any of the commands within the do-done markers, here at least one execution takes place regardless of the control implementation. In all, they have the same type of syntax, but always a reversed logic control. I hereby make once again use of the testing script from slide number 6, this time using an until loop. This loop actually consists of only two commands, one for displaying some output message and the other used for refreshing the control element. As you see, a very simple script indeed with a quite predictable result. So we could go on with our lesson. Like its siblings from the preceding slides, the for do done loop is an iterative sequence with input control. This one is, however, based on a finite list of items, which we will call options or arguments. For the actual implementation, a transit variable is used, which will be repeatedly overwritten until the list is exhausted. Each time the command sequence between do and done is parsed, the var variable is allocated with the value of the next option in the argument list. So in this variable, we will actually have volatile information, which has a per iteration scope. Now, unlike the until and while loops, here is no longer necessary a refresh of the working context. When the last value is finally used, the loop is executed one last time, after which the shell goes over the done line. There are several ways to have such a list generated, as you will see. A hard-coded list of alphanumerical values, a shell-generated list of file names using the star symbol or another meta character, a potentially variable expanded in list of words, or the list of the shell's current positional parameter list, or the same option but in its shell-specific shortcut, and the standard output of an UNIX command. All of these are in POSIX environment eligible options for list of items to pass to a for do done programming loop. The following examples implement all these principles. Example 9.13. assumes the interactive use of the code presented here from a command line terminal. The greater than symbol is the secondary prompt and is meaning the continuity of the command block. This is an example of a list of distinct items, in our case simple characters. The main condition here is to have them separated by one of the usual shell spacers. This exercise works in the same manner, excepting the way we introduce the list of options. While at the previous slide we fed an explicit list of string values, here we can see how this can be done via a simple variable acting as a container for such a list. Finally, we come to the break keyword study. It is found in the internal commands of the shell in association with the programming loops. When the break command is executed, the loop ceases the current execution cycle. The shell moves to the next command line that follows the done statement and continues processing the script. Its usage is quite intuitive, but here comes the interesting part. When dealing with nested loops structures, if the break command is given a positive integer as argument, this number is going to represent the number of nested loops that must be broken. The break command would usually be executed following a conditional test. As I pointed out in a previously commented slide, one of the ways to approach a while loop could use the true command as a control element, which looks potentially dangerous in structured programming. However, a common implementation using a small trick can properly set the logic within the do-done sequence, so it ensures a good functionality. Take for instance this small script where you can see how it's done. The break command is a good friend. It helps a lot when it comes to freeing resources and gaining precious time. Similarly to what we saw in the break command presentation, we have the continue command. When the continue command is used, no matter what the current command position is within the do-done sequence, the shell returns to the start of the loop and re-executes a new loop. Any command lines within the loop following the continue command will be skipped for the current iteration of the loop. If the loop is being controlled by the for statement, the next argument in the argument list will be assigned to the transition variable and the loop will be executed again. If the loop is being controlled by a while or until statement, the conditional test is reevaluated, and if true, the loop will be executed again. As with break, the continue statement can be as well followed by an integer value. The integer value would be the number of nested levels to cease processing before continuing. This is only applicable if there are nested loops in the program. Just for the reference, if ever a numeric value follows a break or continue within a single loop construct, it will not change its behavior, so no danger to feed value to them in case of a single level loops. In order to show how the continue command operates, in this slide I've chosen a stump piece of code from the 8th slide, where we saw the loop control made up from a list of commands. Right, so within the do-done sequence you can spot some standard string extractions from the file name belonging to the current directory, searching a particular set of files whose name end in .ksh. Subsequently, I call the continue command on the else branch, such as to avoid the loss of computing resources for the category of files that is not of my interest. The ubiquitous exit command forces the script to terminate immediately. It can occur anywhere inside a script as well as in the middle of a loop's do-done sequence in order to stop execution upon reaching a certain condition. Despite its simple countenance, the exit command is particularly useful. It helps sending a numerical information to the higher shell instance. Let us give a look at these three scenarios. Like break or continue, it too can be followed by a positive integer value. However, this has nothing to do with nested loops or single level loops, and is only suggested to use values within the 0 through 255 range. This value will actually be the return status value, which is sent back to the parent process. The leftmost one, which is quite common in standard scripts, shows its default behavior. If no number is passed on, it will just propagate the final state of the previous command. The middle version has the same effect except for the explicit assignment of the last returned code, if you recall the $? variable. Finally, the rightmost version shows how the exit command accepts an integer as an input argument. This value will serve as a return code for the parent session. The select loop has a similar construction with the for loop. It is, however, designed as an infinite loop. Each time the interpreter reaches the beginning of the loop, the entire argument list is presented as a numbered list. To be more specific, the contents of the PS3 variable is presented to the standard output as a prompt. When that happens, one of the numbered choices can be selected, and the transition variable will contain that choice for one iteration of the loop. The shell will store the number of the choice in the built-in variable named reply. Be advised, pressing the enter key at the PS3 prompt will cause the loop to start again and again display the whole numbered list of choices. The body of the select loop would normally contain a case statement or an if-then statement to act upon the choice made by the user executing the script. Entering a non-valid number does not stop the loop. Only the end of file character, also known as Ctrl-D, or a break command would do that. Here you have a light implementation of the previously explained theory. A small script which has a list of files generated from the current directory as an options list for our select loop. Note the usage of the read command as a breakpoint in the otherwise rapid iterating process, and at the same time acting as a control element of our select loop. And the effects of this script are displayed here. Within my temporary directory, I only have 11 files with some pretty sophisticated names. Anyway, the thing is that the list command in my loop control line creates this list of names, which is then numbered by the interpreter according to the select loop specifications. I only have to feed a proper number and they play along with my program logic. In the end, when I decide I've done the job, a Ctrl+D input will get me out of this loop. So despite a finite number of possible choices, the select will continue to run until a specific termination command is issued.